In this video, we will talk about titration curves and buffers. So when you perform the titration in the lab, you were adding sodium hydroxide to an acid that was contained in the flask. Now in the lab, you had either oxalic acid or acetic acid from vinegar in your flask, but you had sodium hydroxide in the burette. And you knew that the titration was done when you would observe the changing coloration of the indicator that was phenolphthalein, that initially was colorless and was turning pink at equivalence point. But you had no idea what was actually happening during the titration. So now that we have the concept of pH, and we know that the pH is is minus the logarithm of the concentration of the H+, we can see what's actually happening in terms of pH during a titration. And that could be done by performing the titration while measuring the pH multiple times along the procedure using a pH meter. Obviously, as you might suspect, the pH would be quite acidic at the beginning when you haven't yet started the titration and you have just your acid. In this case, the acid is hydrochloric acid, 0.3 molar in 50 milliliters. So you could, for example, calculate, based on the fact that it's a strong acid, you could calculate the pH. But you may think that the pH is going to change in some sort of linear fashion during the titration, but that's not the case. So here you see the pH at the beginning of the titration where you have not yet added any sodium hydroxide. So the volume of sodium hydroxide added here is 0. And then, as you might expect, by adding sodium hydroxide, you react that with hydrochloric acid. So it's a sort of limited reagent situation where sodium hydroxide is the limited reagent and hydrochloric acid is the excess reagent for the whole titration until you reach equivalence point. That's the moment in which you have, that would be more the final point, but the moment in which you have equivalent amount of moles of H plus and OH minuses. But as you see, the pH does raises, right? Because if the concentration of the H plus goes down as hydrochloric acid reacts with sodium hydroxide, right? So as you are reacting from NaCl that is neutral and water that is neutral, so that's why this type of reaction are called neutralization. So you are pretty much using up progressively the hydrochloric acid, the acidity drops, the pH goes up. So during the titration, the pH goes up, but it does not do this in a linear fashion. Then you could pretty much fit a line here, but then all of a sudden it started changing abruptly. And here we have a situation where just a drop makes the pH jump up to 7, and then quickly another drop would jump it to very basic value. And then eventually, when you are starting adding an excess of sodium hydroxide, you would see that the pH becomes really, really basic, but again, it changes with a much smaller slope. So in the titration you did in the lab, you would stop here. This would be your end point. That's the equivalence point, and if you're quick enough and let's say with some training in detecting the change in color, this is also going to be the equivalence point. There is quite a minuscule difference between the two. But so you would have not continued doing this part of the graph, right? So that is sometimes a bit confusing, because when students see this graph, they tend to assume that this is the end of the titration because it's the end of the graph, and this is somehow the mid point of the titration. In fact, the titration ends here. This is the equivalence point and the end point. That is, for example, in this case, 150 milliliters of sodium hydroxide. At this point, for a strong acid, the pH is 7. So potential question could be questions in which you see a graph and you're asked, but you don't know what's in the burette and you don't know what's in the flask, right? So on the x-axis, you have the milliliter from the burette. Now in the burette, typically you have a strong acid or a strong base. What could be weak or strong is what it contained in the flask. That's what you are not sure about the concentration and what you're trying to standardize. So you're trying to determine the concentration of the content of the flask. And that could be strong, could be a weak acid, could be a strong or a weak base. But what you use in the burette is strong and has a concentration that is known with a good degree of confidence with several sig fig. In this case, 2. In our lab, we had 3 sig fig for the concentration of the sodium hydroxide. On the y-axis, you have the pH. Okay, so you have first choice is figuring out if what you're seeing is a titration of an acid or a titration of a base. If the initial pH is acidic, you're titrating an acid. If the initial pH would have been basic, and you would have a, let's say, mirroring looking graph, that would have been the titration of a base. Then the second question is, sure, I figure out that this is an acid. Is it weak or is it strong? For that, you need to look at the pH at equivalence point. For a strong acid and a strong base, the salt that you're forming is neutral because you have the conjugated base of a strong acid and the conjugated acid of a strong base. So they are both extremely weak based on what we learn. And this makes the salt neutral. This instead is the titration of a weak acid. So I can tell immediately it's acidic, I'm titrating an acid because I start from an acidic pH. But you see that the shape is a little bit different. There is a sort of this change in slope here in this area. So it starts by changing the pH quite quickly, and then for some reason there's something here that's preventing the pH from changing abruptly. It's still changing, but to a lower rate. And then this effect of calming, this calming effect, let's say, we will call it buffering, is going to disappear, and so the pH is going to quickly rise again. And the most important difference, the one that you cannot miss, is that the pH at equivalence point is not 7, it's 9. So for the titration of a weak acid, we are going to have pH at equivalence point that's going to be basic. So that's really the information that's critical to determine if the titration you're observing is of a weak acid over a strong acid. Let's see an example of a weak acid titrated with a strong base. So the acetic acid is in the flask underneath, and we are trying to determine its concentration by using sodium hydroxide that's in the burette, and that's a strong base. So when we go to see what are the products of this reaction, we have acetate ions. That's a base, is the conjugated base of acetic acid, that's a weak acid. Therefore, the conjugated base is relatively strong. However, the base, that's a strong base, hydroxide, its conjugated acid is H2O, that's very weak, so this is not affecting the pH. So the pH is going to be determined by the fact that the sodium acetate is a relatively strong base, therefore the pH is going to be larger than 7. The opposite scenario would be having ammonia in the flask and being titrating the ammonia, that's a weak base, with a strong acid in the burette, as hydrochloric acid. So we would form ammonium, that's the conjugated acid of a weak base, so it's relatively strong. But then Cl- is the conjugated base of a very strong acid, so it's weak. So at the equivalent point, the pH is going to be acidic. This graph is showing you the superimposition of the titration of a weak acid and the titration of a strong acid. So it highlights the difference and the commonalities between the two. So in black, you see the behavior of weak acid that's titrated with sodium hydroxide. In purple, there is the titration of a strong acid, also titrated with sodium hydroxide. So the two graphs are different until the equivalence point. That's 40 milliliters here. After that, the two graphs are identical, so you see only one graph basically. So both acids, you start from the same volume and the same concentration for both acids. So you have exactly the same number of moles of the two. You would have to convert these to liters. 0.040 times 0.1 would give you the number of moles of both. That's going to be identical, therefore they will require exactly the same amount of sodium hydroxide. That would be 40 milliliters. Because the concentration of the base is equal to the concentration of the acid and they react in a 1-to-1 ratio, you will need exactly the same volume of base that you have added of acid, if it makes sense. So what are the difference between these two graphs? It's a very common question. To show you the graph without telling you what's in the flask, and you have to figure out either if it's an acid or a base, in which case, and to answer that, you look at the pH at the beginning. So if the pH at the beginning is acidic, you are titrating an acid. But then they may ask you, well, is it a weak acid or a strong acid? For that, you need to look at the difference between the two graphs, right? So obviously, the strong acid in purple, you're going to start from a more acidic pH because it's stronger, so you have more H+. You have, 100% of the molecule are dissociating, as opposed to a weak acid where it could be as low as 5% of the molecule that are dissociated. That would be the percent ionization, right? The percent ionization for the strong acid is 100%. The percent ionization, let's say acetic acid, would be around 5%. As we've seen, it depends on the concentration. But let's just throw a number just to have a sense of the relative amounts. The other difference is the shape of this of the initial parts of the graph. So for the strong acid, you have a pretty much linear slope, constant slope, so you could almost fit a straight line here. For the weak acid, instead, you see slightly different behavior, because there is an initial phase in which the slope is pretty steep. So adding a certain amount of drops of sodium hydroxide changes the pH quite a lot. Then the pH kind of changes at a much lesser rate, right? So the slope is quite smaller. So that means that there is a resistance in the solution to change pH, despite the fact that we are adding a strong base. So this area that we could pretty much identify as in between these two marks, so between 30 and 10 milliliters. Despite adding, between here and here, you're adding 20 milliliters of sodium hydroxide, the pH changes stays pretty much fixed around 5-ish, so it doesn't change that much. So this resistance to the change in pH is called buffering, and so this is the so-called buffer zone of the curve, and you don't see that for the hydrochloric acid, for a strong acid. But what really gives away the fact that one is a weak acid and one is a strong acid is the pH at equivalence point. So equivalence point is at 40 milliliters. So when you were doing the titration with the indicator, you would know what was the equivalence point because the indicator was changing color. So here you have the pH, not the color of the indicator. So how can you tell where the equivalence point here? Because equivalence point is close to the end point, one of the most common mistakes you can do is thinking that the equivalence point is at the end of the titration, of the graph, right? So although it is formally at the end of the titration, in the graph sits right in the middle, and is the point at which the curve, the curvature changes from being concave to being convex, right? So in terms of reasoning in mathematical terms, it's the point at which you have the maximum slope of the curve, so that would be when the first derivative reaches a maximum and which the second derivative value is 0. And you can kind of eyeball it, so it's going to be different for the purple and the black curve. For the purple curve, it's going to be there. And for the black curve is going to be there. So What this is telling you is that the pH for the at the equivalence point, the pH for the weak acid titration is going to be basic. And that is because you're forming the conjugated base of a weak acid, so let's say acetate, so that's going to make the pH basic. For a strong acid, the conjugated base is extremely weak, so it doesn't affect, so you get a neutral salt. Therefore, the pH, the equivalence point for a strong acid, is going to be 7. So that's the really key concept that allows you to identify, and without any fear of mistake, if it's a weak acid or a strong acid. Weak acid equivalent points, the pH is basic. Strong acid at equivalence point, the pH is neutral. For a weak acid, so for the black curve, you also have another important point, that is the midpoint, right? So if the equivalence point is 40 milliliters, the midpoint is 20 milliliters. Why is that important? Because at that point, if you look for the pH, the value of pH corresponds to the pKa, so minus the logarithm of the acidity constant. So if I want to determine experimentally the acidity constant for let's say acetic acid, I can do a titration, build the graph, and then look for the midpoint and for what is the pH at midpoint. And I would get, let's say, a value of 5, so I would know that the Ka is 10 to the minus 5, if it makes sense. Now, in terms of how to determine the midpoint, as I said, either you're doing the titration and recording the data with the software that allows you to calculate the derivatives, and so you then are going to look for the maximum value of the first derivative and the 0 value of the second derivative. Or you can do, there is a graphic method, so you can plot your graph, and then with a ruler and a pencil, you're going to, so let's get black, you're going to draw a black line that best fits this part of the graph, and then you're going to do the same at the top here. Now this is a bit awful, okay, and then you're going to try to draw a vertical line through the middle part of the graph. And so you will see two intersection points here and here. With your ruler, you're going to measure how long is that segment, and you're trying to find the half, the middle of that point, and that's going to be your equivalence point. So why is it that the pH for a weak acid, the pH at midpoint is going to be equal to the pKa? So let's consider our titration of the weak acid. And let's imagine what happens when we are added only 50% of the sodium hydroxide that would be required to complete the titration. So it's a bit like a limiting reagent problem. Sodium hydroxide halfway in the titration is the limiting reagent, and HA is the weak acid, is the excess reagent. Okay, so let's say when I start, I have all my acid because the reaction hasn't started yet. I have not added yet any sodium hydroxide, so the amount of sodium hydroxide is 0, and I haven't yet made any of the products. I had 50% of the total amount required of sodium hydroxide. So it's a limited reagent problem. So they react to 1-to-1 ratio, so that would use up half of the HA, and I would make half of the total amount of salt and water that I would make. Not that water is of any interest here, I have a beaker full of water, right? So at this point, I have because my weak acid is in excess, I'm going to have 50% of the acid left. There's going to be no sodium hydroxide left because I use it at all. And I will also have made half of my salt. So that's the part that is interesting. At midpoint, the amount of acid that's left is exactly identical to the amount of conjugated base made. So we can consider our acidity, the expression for the acidity constant, right? So if we were able to calculate this, this is related to the pH. So that's what we are going to figure out. Now, the concentration of conjugated base and acid, these are that I can plug into the Ka to calculate the pH. Those are the concentration and equilibrium. These concentrations are different from those. So even if I know the actual number here, let's say I started from 2 molar, so this is 1 molar and this is 1 molar. That's going to be diluted, so there is a further complication in the calculation, but that doesn't matter. The problem is that I have equilibrium going on, right? So I have these two equilibrium going on. My weak acid is going to react with water, forming A minus. And my A minus coming from here, from the product of the titration, is going to react with water, forming HA. So it's quite complicated. But because basically one thing goes opposite of the other, and these changes are minimal, I could simplify my life and say, sure, in theory, I know, because I did my homework, and I know that here I have to put the concentration at equilibrium. But I could make a simplification and think, well, this concentration and equilibrium are not so different from the concentration, from the total concentration, let's say. All right, so I can just plug those numbers and call it a day. In which case, whatever are the numbers, the key thing is that those numbers are identical. So that means that the amount of this and the amount of this are going to be identical. That means that I can simplify. So you see that the Ka becomes equal to the concentration of the H plus. Therefore, if I calculate the logarithm on both sides and I change the sign, I get that the pH is equal to the pKa. And that's the experimental way to determine the acidity constant of weak acid. So what is a buffer and how does it work? A buffer is a solution that contrasts and resists a change in pH. So if we have a glass of water and it's just distilled water, and we add in even just a drop of a strong acid or a strong base, the pH will change dramatically. But if we have a buffer, the pH change will be really, really small. It would still change a little bit, but of a very small number. And what makes a buffer? What does it take to make a buffer? You need two things. You need a weak acid and its conjugated base, or a weak base and its conjugated acid. So it's a bit like defending a castle. And you know that you're going to have, you need two defenses line, because you may be attacked by the acid, strong acid, or you may be attacked by the strong bases, right? So you need the two defenses line to be equally strong. So if I'm taking a weak acid, HA, then the conjugated base A minus is going to be quite strong, so it's effective in defending me from the HCl attack. But if, for example, I would take hydrochloric acid, that's a very strong acid, so I would have an effective defense line on the right. But on the left, I would have Cl minus, that's the conjugated base of a strong acid, therefore extremely weak, so that defense line would be overcome immediately, overturned immediately. So you need a weak acid and its conjugated base, or a weak base and its conjugated acid. So if you're adding a strong acid, the strong acid will react with the conjugated base, forming a weak base, a weak acid. So that's why you are converting from strong to weak, therefore decreasing the effect. If you're adding a strong base, that will react with the weak acid component of the buffer, forming a very weak acid. So again, you're converting something strong into something weak. So the ideal combination of the two is also to have the same amount in moles, to have the same quantity of this weak acid and its conjugated base, or weak base and conjugated acid. That would be like having the same amount of soldiers here, right? And why is that? Because in that condition, I can buffer the same extent of addition of acid or base. So how do we calculate the pH of a buffer solution? So there is a special equation that makes it quite quick and simple, and it's called the Henderson-Hasselbalch equation. I'm going to show you how to derive it, that you don't have to do, because you are going to be given the equation in the exam cover. However, the reason you want to, if you understand where it's coming from, you understand how to use it. Also, keep in mind that very rarely in the problem you will see the word buffer. If you would see the word buffer in the question, you would know immediately that you have to use the Henderson-Hasselbalch equation. But then life would be too simple, wouldn't it? Right? So most of the time they don't tell you it's a buffer, and the expectation is that you should pay attention to what you have in the solution, and whenever you see that you have a weak acid in the presence of its conjugated base, you should assume that's a buffer and use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is just obtained by some simple algebraical passages starting from the equilibrium constant. So we have the equilibrium constant for the dissociation of the weak acid. We solve for H+, right? So we said the perfect combination is when the conjugated acid and the weak acid and its conjugated base are present in the same amount. Now, because this is an equilibrium constant, you would have to enter here the value at equilibrium that are not the total value of the species, right? However, we can simplify and assume that there is not a huge difference between the equilibrium level and the total amount, so we can just plug directly the initial amount into the equation. So that's going to make the math much simpler, even if not formally perfectly correct. So once you have solved for H+, you calculate the minus the logarithm on both sides of the equation, and then you will end up with minus the logarithm of HA over A minus. So people prefer plus sinus to minus sinus, and so you can, to do that, if you could change the sign, you need to flip the fraction here, so HA goes on top. This is also, so it's sometimes it's written like this, sometimes it's written base over acid, sometimes it's written salt form over acid form. So let's see how to use it to calculate the pH. So let's see some example of calculations with the Henderson-Hasselbalch equation. So for example, you have these three buffer solutions. They are all made with acetic acid and sodium acetate. You are given the equilibrium constant for the acetic acid. So you just have basically to plug the numbers in the equation. Now, first, a couple of notes. First of all, this is a very nice way of wording it. They are actually using the word buffer. Do not expect that to be always the case. Most often than so, you will not see the word buffer at all, and you have to figure it out so you know which equation to pick. So you know it's a buffer because you have weak acid and its conjugated base, okay? And you need to calculate the pH. So you're taking the Henderson-Hasselbalch equation in any of these forms, and you are plugging in the concentration. So you need to, first thing, you need to figure out which one is the acid, which one, that would be HA, which one is the conjugated bases, so you don't risk to flip the numbers in the fraction. So the acid is always the one that has an extra hydrogen in the formula. So in this case it's relatively easy, which one is called acid, so you have acetic acid and sodium acetate. There are situations in which it's less obvious, so look for the formula and identify which one has one extra hydrogen with respect to the other one. That's the acid. Finally, concentration to plug into the equation. if you you would have to plug in the equilibrium concentration that you don't know, because these concentrations are the initial concentration, the total concentration. Okay, we do the simplification that even if that's not formally correct, we are not introducing a huge error, but we are simplifying enormously the math. So we are going to plug in an equation that's coming out from an equilibrium from an equilibrium expression, concentration that are actually initial concentration. We should be aware that we are doing something that's not entirely proper, but we are confident that the error we are doing is not going to be significant. So I'm going to give you some minutes to try to do the plug and chug, and then we are going over it and see a couple of things. So for the first one, right, you have equal concentration of the acid and the conjugated base. So you end up with the logarithm of 1. The logarithm of 1 is 0. Therefore, the pH for that particular scenario is going to be equal to the pKa. So 4.752, it's minus the logarithm of 1.77 times 10 to the minus 5. Okay, so if you have the Ka minus the logarithm of the Ka correspond to the pKa. The second buffer, the difference is that you have less acetic acid. Because the acid goes underneath, that means that you are ending up with a logarithm of a number that's larger than 1. The logarithm will therefore come up positive. So you are adding something on top of your pH. So the pH should be higher than the pKa, because you're adding something on it, and in fact you get 4.849, so that's a little bit more basic. That makes sense because you have only 0.8 of the acid component of the buffer, but you have 1 of the basic component of the buffer, so it's more they say skewed toward the basic side of the buffer. Third example is the opposite. In this case you have more acid and less base. So because the base goes on top, this time the logarithm is going to be the logarithm of a number that's lower than 1. The logarithm will come up negative. So you're taking away something out of this 4.752. In fact, the pH will come up around 4.6, so more acidic. That makes sense because this time you have more acetic acid than base, sodium acetate. So the buffer range is that range of pH in which the buffer is working well, and that corresponds pretty much to have a ratio of base to acid of 10 to 1. So the ideal spot is having your defenses equally strong on both sides of the castle, so 1 to 1. If you can have 1 to 1, 10 to 1 or 1 to 10 will still work. So based on the math that we just did in the other example, that corresponds to 1 unit above or below the pKa. The buffer capacity is how many moles you actually have of the weak acid and the weak base. So that would be how many soldiers you have on each side, right? And so and the importance of the. So let's go over the concept of capacity of the buffer with this problem. We have 1 liter of each of these two different solutions. Solution A is 0.10 molar in dihydrogen phosphate and is 0.20 molar in monohydrogen phosphate. So this phosphoric acid is a triprotic acid. So it could lose 1, 2, or both, or all of the 3 hydrogens, so you can have multiple salts. And it's important because the monohydrogen dihydrogen phosphate buffer is one of the buffers in the mammal's blood. Solution B has the same compounds but a different concentration. So the first question is, what about if we compare the pH? Do they have the same pH or not? So we can use the Henderson-Hasselbalch equation. And we can see that the ratio between the base and the, although the absolute amounts are different, they are both in a ratio of 2 to 1, where the monohydrogen phosphate, so this one, that is the base, right, because it has one less hydrogen, the monohydrogen phosphate is going to be twice as much as the monohydrogen phosphate, that is the acid, and you have less of that, okay? But the ratio is the same, so when you go and divide in this expression, for both instances, you put the base on top. The base is 0.20 divided 0.1, it gives you 2, or 0.30 divided 0.15 is still 2. So you get logarithm of 2 in both instances. Therefore, the pH is going to be the same. So the correct answer is this. Which solution will be able to neutralize 0.11 moles of sodium hydroxide? Okay, so you have 1 liter of the solution. For sodium hydroxide is a strong base, so it will react with the weak acid in the buffer. The weak acid is H2PO4. But in solution A, you have the solution A is 0.1 molar. So if you have a 1 liter, you have 0.1 moles. So you will not be able to neutralize all 0.11 moles because you have only 0.10, right? So as you will not have this problem with solution B because you have 0.15 moles per liter. So only solution B will be able to neutralize it. If we have the same amount, 0.11 moles of a strong acid, in this case, the component in the buffer that will react with the ACl is going to be the weak base, so it's going to be the monohydrogen phosphate, for which I have 0.20 moles per liter in solution A and 0.30 moles per liter in solution B, so both are larger than 0.11, so both will be effective into neutralizing that. Now, what can I say about the buffer capacity? I can say that B, because it has a larger absolute amount, even if it has the same pH, has a higher capacity. So now that we have several formulas involving the calculation of the pH, let's just do a recap and see when to use certain formulas and when to use others. So if you have a problem where you need to calculate the pH, have a look at the substances. Is there only one substance that is either acidic or basic, or is there more than one? So if there is only one substance, it could be an acid or a base. So let's just stick to the acid. Is it going to be weak or strong? So if it's a strong acid, that's the easiest scenario because it's completely dissociated. So for a strong acid, the concentration of the H plus is going to be identical to the concentration of the acid. So to calculate the pH, all you have to do is take the concentration, calculate the logarithm, and change the sign. If it's a weak acid, then you have to use an IC table, okay? And if the concentration of the acid is more than 400 times larger than the Ka, then you can do that simplification, so the formula becomes quite simpler. And once you have the concentration of the H+, you just use the formula for the pH. If you have a base, you just need to remember that the pH is going to be equal to 14 minus the logarithm of the OH minus. So you would calculate the concentration of the OH minus, then you can calculate the POH from that, and then from that you can calculate the pH. If you have two substances, you have a buffer. Likely. So check if it's a buffer. Are those two substances a weak acid and a conjugated base, or a weak base and a conjugated acid? If the answer is yes, then you have a buffer and you have to use the Henderson-Hasselbalch